So yeah, so last class we were in the middle of talking about oscillation, and pretty much the last thing that we did was talking about the velocity equation and the graph that we came across. And basically, the equation that we didn't derive, but yet did somehow logically prove is this one, right? And how so? Basically, we talked about how velocity can be expressed in terms of the position of any oscillating object. What we did basically was we looked at this pendulum example and we were saying, well, if my pendulum is oscillating left and right, and it starts off over here, right? Starts off over there with the minimum velocity or zero velocity, because momentarily at the maximum position, it comes to a stop, or it has the highest amount of potential energy. Why? Because it has been displaced from this position upwards, right? So in a typical pendulum example, what we see is when it reaches the maxima on this side, that is the right hand side or the left side, whenever it reaches this maxima, what we see is it momentarily stops, right? It can be projected very simply with a projectile motion example. When it goes up, it momentarily stops, changes its direction, and falls down, right? So it's a very typical example, and holding on to that thought, we apply the same logic over here with case of the pendulum. Whenever it's at the maxima, momentarily stops, starts swinging leftwards, and at this middle ground, at the middle position, we have maximum speed. Why? Because all of that potential energy that you have over here translated into kinetic energy, right? So that potential energy that was gained at this maximum height transferred into kinetic energy. And what do we know about kinetic energy? K is half mv squared. The Ke increases, hence the velocity increases. And when is the Ke max? At the middle ground. Why? Because it's the lowest position. All of that potential energy gained in this height transferred into kinetic energy. So velocity is maximum, right? So now we understand over here, Ke is 0. So at position 1, Ke is 0. Potential energy is max. So this is, if I define right as negative, right, I'm defining rightwards as negative direction and leftwards as positive direction. Okay. So at a at a negative displacement maxima over here, I have Ke as 0 and potential energy as maximum. At the middle ground, position 2 and 4, I have Ke being max, right? And I have my potential energy being 0. Now, the potential energy, the reason I call it 0 is because I'm considering the lowest position as the reference point. I'm simply saying this is my starting point, and over here I consider my bob to have a 0 potential energy. Yes, any question? Okay, so basically what I'm considering is at the lowest position I have minimum energy or minimum potential energy. Why? Because I'm considering the lowest position as my reference point. Okay, so this is my reference point or the lowest position where mgh is considered to be 0. Okay, so basically I consider this as height is equals to 0, and any point upwards of this I consider it to be a positive height. Let's say if it's this much above the reference point, I can say it's 1 meters above, or this is the position 2 meters above, if this is the position 3 meters above, so on and so forth, right? So at the reference point that I have set over here at the equilibrium position, this is my lowest potential energy or potential energy of 0, which h is 0 because h is 0. So what do we understand till now? At position 1, I have kinetic energy being 0, potential energy being maximum. At the middle ground, I have kinetic energy being maximum, but potential energy being 0. Come back to the maxima on the other side, that is left-hand side, that is the positive side. This is the key that I have set for this example. So what happens over here at position 3? What happens over here? I have my KE being what? 0 again. Because at every maxima, this is a maxima on the positive side, this is a maxima on the negative side, right? At the maxima, every single time I have my kinetic energy being 0 momentarily at the maximum position. That means it momentarily stops over there. Okay, it momentarily stops over there at the maximum position because initially it moves this direction, but then it changes the direction and comes back to the equilibrium position. So this change in motion causes the bob to momentarily stop. Hence, K is 0, potential energy is what? If you've guessed maximum, correct. Why is it maximum over here? Not really. I am just revisiting what we talked about in the last class. So yeah, at the position 3, my potential energy is max. Okay, potential energy max. Why? Because it is at the maximum height above the equilibrium position. So where is my bob? Somewhere over here, right? So this is at the same position. So one is maxima on the left side, one is maxima on the right side. Perfect. So based on all of those conclusions, sort of qualitatively made, we didn't do a quantitative derivation of the velocity formula, that is this formula. We made a qualitative derivation, that is we graphed on this y and x axis. On the y axis, I hold my velocity, and on the x-axis I hold my displacement, right? So how does the velocity change of the pendulum with respect to displacement? Okay, and what do we realize? At maximum amplitude or positive amplitude, which is this position, because I've set the left direction as positive. So at this position, what do we have? We have the velocity being 0, right? Because it momentarily stops at the maxima, right? So at the maximum displacement or the positive maximum displacement, 0 velocity momentarily. Hence, we cross this point or plot this part. Next point, let's say this one, right? This one. What happens over here? I see this amplitude is 0 or position 2. Let's mark position 2 over here. What happens at position 2? At position 2, what happens is it has maximum kinetic energy. So if this was my position 1, where it's moving in the left direction, right? At position 2, it is still moving in the left direction with the maximum velocity. Because remember, all of this potential energy transferred into kinetic energy at this lowest position. So maximum velocity. And in what direction? Leftward. Is left positive or negative? In our case, I've considered left to be positive. So hence you have Vmax over here at position 2. Since leftwards, hence on the positive y-axis. So at my displacement is 0, that is my equilibrium position on the pendulum diagram, I have my maximum velocity. That is this. Now, let's say at position 1 again, which was the initial starting position. Sorry, I started from position 3, just to explain. But anyways, at position 1, which is the starting point, it is moving leftwards. But the displacement from the equilibrium at position 1 is what? Right of the equilibrium. What is this displacement? Notice the cursor. It is rightward from the equilibrium position. And what have I set as the right direction? Negative. So since this displacement that is right from the equilibrium, this is the equilibrium, right? This is the equilibrium. So this displacement that is right from the equilibrium will be defined as negative. So at negative amplitude, that is the maxima over here, that is the maxima over there, it will have what? What velocity will it have? 0, simply 0. So at negative amplitude, I have my velocity being 0. Why? Again, momentarily stops at the maximum position. Same logic. And at position 4, what is it? At position 4, it's simply that from position 3 to position 4, this is the traveling trajectory. So it's going from 3 to 4. And what happens in this case? It is simply coming back to equilibrium or traveling rightwards. So in what direction? Negative direction. So the velocity's direction is negative, and the displacement at position 3 was positive. So for the displacement at position 3, what was the amplitude? Positive. Why? Because it was left from the equilibrium. This displacement is left from the equilibrium. That is why at position 3, I marked the amplitude as being positive. Right? That's the reason. Now, look. I'll undo. Okay. Fair. So now the position 4 that I have, what is position 4? It has come back to the initial equilibrium position. So over here, what happens? If the velocity direction is in what direction? Leftwards. What have we classified? Sorry, rightwards. What have we classified as right? Negative, right? Notice negative. So at position 4, my velocity will be maximum because this is where kinetic energy is maximum. Because all of that potential energy transferred into kinetic energy at the lowest position, right? So it's simply a game of transfer of energy. So basically, at position 4, again, I have the maximum velocity, but in what direction? In the rightwards direction. Hence, we classify this as negative. Now, you may ask me, what would happen if I define this as being positive and this as being negative? Same thing. You would come to the same conclusion, same graph, same everything. Nothing would have changed. Nothing would have changed. You can try it on your own and plot a graph, that is, plot the 4 points, and you will see it will yield the same elliptical shape. Okay? So when you join these 4 points, right, these red crosses over here, when you join these points, it creates this ellipse or elliptical shape. And this becomes a graph of velocity versus displacement. And showing this, looking at this, we can simply sort of agree that this must be the equation of velocity with respect to displacement. Now, if you want to know how this velocity came out to be, this equation came out to be, this is the derivation. You can look at this. You can take a screenshot or look at video 17.5 that is on our channel, and you'll get the detailed insight of how we have derived this final equation after going through all of this. Okay. The reason I have not covered this with you guys because it is not directly in your syllabus, and this derivation will not be asked because it needs calculus to be involved. That is, you need to integrate certain things, right? And that is not in your syllabus, so you don't need to do that. Integration in some places, but not over here. You don't need to derive this velocity with respect to displacement equation. So I'm not showing this. But if you're interested, you can look at this. No worries. So basically, we came to the conclusion that velocity versus displacement graph would look something like this. By qualitatively understanding how my potential energy and kinetic energy changes with position, right? Now look at this equation. I have classified or explained this equation, written this equation as, sorry. Yeah. So the equation becomes plus minus omega times root over maximum amplitude minus displacement. Okay. So if you plot this somewhere, if you do plot this somewhere, you will, let's say, what can you use? Desmos. If you have seen the Desmos calculator, if you plot this there, you will see the exact same graph pop out. So if you just put in omega as any random value and x naught as any random value and type in a equation such as this. So let's say I take omega as 7, root over x naught, let's take 10 square or 10 simply, x square. And if you try and plot this graph in your Desmos calculator, online, website, anywhere, you will see this elliptical shape come up. Okay? You will see this elliptical shape come up. Great. So this is how the equation for velocity looks like. Basically, we are plotting velocity with respect to displacement. How velocity changes with respect to displacement. And the last thing I'll mention, why is this plus minus here? Because with every possible answer that you have, there can be two velocities or velocity direction. What's this? What that means is, let's say, well, I have a displacement of 5 meters. I don't know if it is left or right because look, whenever you put in -5 or 5 over here, this is where you put in your displacement. Basically, the position where you want to find out the velocity, right? So over here, when I put in -5 or 5, it ends up being 25 because -5 squared is 25 and 5 squared is also 25. So whenever I put in any distance value in this place, in this variable, what happens? I get two possible answers. One, let's say this is 5 meters, the other is -5 meters. So, sorry, let's say this is 5 meters. I get two possible answers. One is this and one is this. Okay. There are two possible answers. One is with positive velocity, the other is with negative velocity. Why is that? Let's say at a positive displacement, let's mark that as this position because this is what? At what direction is this from the equilibrium? This is at a positive displacement away from the equilibrium. Okay. Why? Because I've classified left as positive. So this, let's say, has a 5 meter displacement away from the equilibrium. Now, my question to you is, how do you know if this bob is coming back or going to position 3? Do you know that? Nope. I just know that it is at the position of 5 meters of positive displacement away from the equilibrium. Okay. But I don't know if the bob is coming back or going to position 3. So it can go this direction or this direction. I don't know. Do we? Nope, we don't. We do not. Just by defining displacement, you don't define the direction of velocity. Okay? So it could be that bob is going from 2 to 3 or 3 to 2. If it's going from 2 to 3, that is this direction, what happens? My velocity is positive. But what happens if it's going from 3 to 2? My velocity is negative. So the possible outcomes that you have in terms of the velocity are two. One will be positive velocity, one will be negative velocity. That is why you have a plus minus in front of the omega. Okay? This is why you have the plus minus. So I'm explaining everything somewhat qualitatively. I've been showing you the equation, but this is why you have the plus. Yeah.
Could you explain that again? Why there's plus minus?
Because when, let's say, I have this equation, V is equals to plus minus omega root over x naught square. You know what x naught is? X naught is the amplitude of the entire system. So this position is the amplitude, position 3 and position 1. One is negative amplitude, one is positive amplitude. So now let's say the question tells you, I want to find out the velocity, or you want to find out the velocity at displacement is equals to 5 meters. Okay. So what is 5 meters of displacement? It would be somewhere around here. This would be positive 5 meters of displacement because this is leftwards. So left we consider positive over here. So displacement is left of the equilibrium. So positive 5. Now, if I plug in 5 over here, right, what do I get? Omega is equals to plus minus, sorry, velocity is equals to plus minus omega times. Let's say the x naught value or the amplitude is 10. So 10 square minus 5 square, v is equals to plus minus omega times 100 minus 25, 75. So 75. This is my velocity value. So it could be positive 75
Root
omega
over
or
75,
negative.
you said?
Yeah, sorry.
Root over 75? Will it be root over 75 or?
I couldn't understand the question. Sorry. Could you repeat?
Won't it be root over 75?
Yes, it will be root over 75. Yes, my bad. Root over 75, correct. So ultimately, the conversation becomes that this plus minus basically means that it can be positive root over 75 omega or negative root over 75 omega. Why is that? Because at this position, at this displacement, it could be that the bob is moving in this direction or in this direction. Why do I say that? It could be that 5 meters of displacement, positive displacement, denotes a position where the bob is going from position 2 to position 3. that is moving leftwards. And moving left is
Positive.
positive velocity. And it could also be, it is going from position 3 to position 1, hence backwards to the equilibrium. And what is this? Moving right is negative. So two things can happen: coming back or going to the position 3, right? Coming back from position 3 or going to position 3. So in those cases, it gives me two different velocities in terms of direction. So how do we denote that? We say plus minus root over 75 omega. It can be positive direction or negative direction. Do you get that?
Yes.
Perfect. So that is ultimately the crux of the equation, how we use it, why it makes sense, qualitatively explained. Okay, so just be get used to how to plug in the values and get used to this graph. This graph is important, right? And I've explained why it makes sense with respect to the displacement. If you plot it out yourself, you'll see that as well. Now the question becomes, a conversation becomes that how does the energy vary? And I also talked about how the energy varies over here. So if we just shortly give you, if I just give you a short glimpse of this, I covered in last class. What happens is the same conversation of position 1 has max PE, right? And 0 KE. Why 0 KE? Because momentarily stops. And at position 2, I have 0 PE, potential energy, and max KE. What happens at position 3? Same thing as position 1. So max potential energy, because it is at a maximum height, and KE is equals to 0. So what we realized is when we plot the kinetic and potential energy, we get something like this. So this is the kinetic energy against displacement. At my displacement is 3, that is this one, I have 0 kinetic energy. And at position 1, I have 0 kinetic energy. When do I have the maximum? At position 2. And when I connect all of these points, I get something of a semicircle, right? When I connect these 3 points, I get somewhat of a semicircle. Fair enough. And when I do the same with potential energy, I have maximum potential energy at position 1, sorry, position 1 and at position 3. So maximum over here. And what is the 0.0 potential energy at the equilibrium position? Why? Because all of that potential energy converts into kinetic energy. So this is where my KE is simply 0. Sorry, KE is, my bad, max. And potential energy is 0. Okay, so all of that potential energy basically transferred into kinetic energy. Okay, so that's perfect. That is how the transfer of energy works. So now what happens if I combine these two graphs? Look at this. I have combined the kinetic and potential energy graph, and what I see is I get a bit of a total energy line. What does that mean? Basically, when my amplitude is, sorry, displacement is maximum or at negative max displacement or negative amplitude, right? At this position, what happens? Your kinetic energy is 0 because momentarily stops, and potential energy is max. So let's note this. Your yellow line is the potential energy, your red line is the kinetic energy. If I add 0 plus whatever the value of potential energy is, I plot an orange point over here. That is the orange line, a part of the orange line. What happens when I have, let's say, somewhere in the middle ground, where my kinetic energy and potential energy is somewhat equal? So basically, if I am at negative amplitude, that means this position. So when it's coming back, at some point, the kinetic energy and the potential energy of the bob is equal. Why? Some of that potential energy that the bob has over here is transferring to kinetic energy. While that transfer is taking place at some position over here, potential energy equals kinetic energy. That is what we observe over here at some displacement x. At some displacement x, negative x that is, we have the potential and kinetic energy being equal. And when we add these two up, I have this point, which is again the line of the total energy. Let's see at the middle ground, the middle position, equilibrium position. This is the EQ position. What happens here? My kinetic energy is maximum. See the red line? that is a maxima. See the yellow line, that is zero. What is the yellow line? The potential energy, right? So zero plus maximum kinetic energy gives me again the total energy. Okay, so whenever you add these 2 points on these two graphs, it gives me this orange line over there at the top. Why? This orange line is basically total energy of the bulb or the system. Whenever you add both kinetic and potential energy, that gives you the total energy of the bulb. That never changes. Never changes. Give me a yes or no or a thumbs up. That is, can I say this? Can I say this? K max is the total energy of the system. Give me a thumbs up if this is right. Whatever the maximum value of kinetic energy is, that is over here at the equilibrium position, equals to the total energy of the system. Give me a thumbs up if you agree, or thumbs down if you don't agree. Quick. Okay. Others? Look at the graph. Yeah? What do you think? Is K max, the maximum kinetic energy value, equal to whatever the total energy is? Okay. Mm, uh, okay. Yeah. So yeah, technically speaking, yes, this is right. Whenever you have this statement that kinetic energy, maximum kinetic energy, equals to the total energy of the system, in this case, yeah, it is right. Because when do you see the maximum kinetic energy? Over here, at the middle ground, where my potential energy is zero. And what did we say? The sum of kinetic and potential energy always gives me the total energy, which is a constant throughout the journey. Which is a constant throughout the journey. So at this equilibrium position where my kinetic energy is max and potential energy is zero, it essentially means that Ke max plus Pe, which is zero, is total energy, right? So if P is zero, then can I not say that kinetic energy is equal, sorry, maximum kinetic energy is equal to total energy? Yeah, I can. Now, next question is, can I say the potential energy max is equal to the total energy of the system? Give me a thumbs up if you agree. Can I say this? Okay. So, wait, give me a moment, please. Right. So, yes, it is correct. This statement is also correct. Why do I say that? Because notice when the potential energy is maximum. At, where did it go? Oops. So at this position, right? See this line? At this position of negative amplitude and at this position of positive amplitude, my kinetic energy is zero, but my potential energy is max, right? So over here, when you're saying PE max plus KE, sorry, PE max plus KE is equals to total energy, what happens at the amplitude position? My PE max is maximum and kinetic energy is zero. So that means my potential energy maximum value is simply equal to the total energy. That is it. Very simple. So at these two positions where my potential energy is maximum, that simply means that whatever the energy value is there, of potential energy directly equals to the total energy of the system. And total energy remains constant throughout the journey. Okay, fair enough. Now, prolong that idea to an extent and understand that energy changes with respect to time, that is, individually. Kinetic energy changes with respect to time or position, and potential energy changes with respect to time or position, right? So if the position is changing, that obviously means that time is also progressing, right? If time is progressing, that also vice versa means position of the bob is changing. Both are, it might mean the same thing. So basically, if with respect to displacement, I can say that my energy is changing, I can also say with respect to time, my energy is changing. Individually, that is, kinetic energy wise and potential energy wise. Does the total energy change through the journey? Give me a thumbs up or thumbs down. Yes is thumbs up, thumbs down is no. Does the total energy change with respect to time of the system, of the bomb? Yes or no? Perfect. So my total energy never changes. It is the sum of Ke and potential energy. Okay? Never changes. Fair enough. Now look, the same thing that I did with energy versus displacement, let's do the same thing with energy versus time. The thing with time is it is not limited between a maxima and minima. That is, displacement is limited between minus A and positive A. So it can go till maximum amplitude and minimum, sorry, zero amplitude and maximum amplitude, right? So it can go to negative max, positive max, and zero. So this is pretty much the region with which we play with the graph, right? We plot from negative amplitude to positive amplitude and zero. With that is energy with respect to displacement. What happens if I want to do the same thing? I want to plot the same energy versus uh, I want to plot the same energy but versus time. What happens in that case? We want to take you back to the velocity with respect to time equation. If you remember correctly, velocity can be explained as v is equals to a omega cos omega of t. Okay, this was the equation where a basically means maximum displacement. So I can also write this as v naught cos omega t. Why can I write this as v naught? Because a omega is the amplitude of this trigonometric function. How much does cos omega t vary? Between what values does cos omega t vary? Cos varies between -1 and +1. So what is the maximum velocity possible out of this equation? A omega. When cos omega t equals to 1, I get the maximum velocity, which is a omega. So I can simply say a omega equals to v naught or maximum velocity. There's another way to explain this. Yeah. So there's another way to explain this. That is, from circular motion, v is equals to r omega, right? So when r increases, that is, the displacement increases to a maximum value. That is, I can say v is equals to a omega amplitude. I get the v max value. So when you're increasing the r of the displacement to maximum, that is the amplitude value, v is maximum. This is another way to explain it from circular motion. If you don't remember circular motion, fine, no worries. So now, coming back to this, how do I plot velocity versus time? Velocity varies from positive maximum to negative maximum as a cost function. Okay, so it goes from, if I define this pendulum, so this is my position 1, let's say, where it's starting from, and over here, sorry, this is my position 1 where it's starting from. So the equilibrium position is where my bob starts oscillating from. And over here, what do we know? The velocity is v is max. Why? Ke is max. Okay, so this is the position, the equilibrium position or the starting position. we have maximum velocity. This is why we have a cost function, because at phase of 0 or 0 degrees, we have maximum velocity, right? So it starts off with a peak and travels below. This is around, let's say, 180 degrees. And this is again, the peak comes out at 2 pi or 360 degrees, right? We had this elaborate discussion in some of the previous class, last class or last class. But basically, this is how velocity versus time graph varies as a function of a omega cos omega t, right? Granted, you understand this. Can we now plot the kinetic energy graph? What do we know about kinetic energy? Well, Ke is equals to, by the way, this is velocity with respect to time, right? Hopefully you understand that. And kinetic energy, what is the equation of kinetic energy? Half mv squared. Do we know this? Yeah, we do. Can I plug in V over here? What is the equation of V? This, right? Fair enough. Let's plug that in. So Ke, I can say half m a omega cos omega t whole square. And that ends up being K is equals to half m a square cos square omega t, right? So this now becomes my kinetic energy equation. This is how my kinetic energy varies with respect to time. Clear? This is how my kinetic energy varies with respect to time. So what is the equation that I get? This. This is exactly what I've written over here. Okay. So what happens if you plot this? This is a typical cos square trigonometric curve or graph, whatever you want to say. So when you put this in a Desmos calculator, wherever you want to check it out or verify yourself, which one is it? Pink one. The pink line that you see, this one, is the cos square curve, right? The one I just highlighted with white. So that is your kinetic energy with respect to time. How the kinetic energy varies with respect to time. How did we get this graph? We just derived it by plugging in velocity into the equation. And we saw that kinetic energy varies with respect to time as a cos square function. Now, there's another qualitative answer to this. Why does it never the x-axis, sorry, yeah, the x-axis and go to the negative axis over here, negative y-axis? Why is there no part of the graph in the negative axis? Why? Simple answer. Energy is never negative. Clear? Energy is never negative. So talk about kinetic energy, talk about potential energy, none of them are ever going to be negative. So what is the variation possible? Kinetic energy can vary from 0 to a max value that is positive. Potential energy can also vary from 0 to another max but positive value. So this is the bounds of the kinetic and potential energy, varies from 0 to a maximum value. That is it. That is pretty much it. Now, what happens with the potential energy curve? Let's see. So, you know the total energy is a sum of kinetic energy and potential energy, right? Great. Can I write the total energy as half m a square omega square? Yes, I can. Why? Right before talking about this, we had a discussion that I can define the total energy as Ke max, right? And you all agreed with me. I can define total energy as Ke max, or I can also define total energy as Pe max. Whatever the maximum kinetic energy the bob can have, and whatever the maximum potential energy the bob can have, both denote whatever the total energy the system has consistently through the journey. Okay? Okay. So now can I define the total energy as Ke max like over here? Yes, I can. And but by the way, what is the maximum kinetic energy? The maximum kinetic energy is simply this. How, you ask? Look, this is the kinetic energy formula we found out over here. I'm simply going to replace cos square omega t with 1. Why? Because when do we have the maximum value of kinetic energy? If cos square varies from 0 to 1, by the way, cos square varies from 0 to 1. If you guys don't know, well, this is a cos square curve. This is a cos square curve. Okay. And let's say t. So the cos square value can only vary from a maximum value, positive maximum, to 0. It cannot cross the x-axis and go to the negative y-axis. Okay. So if you have worked with square trigonometric functions, you know that there can't be negative values. Okay. So you have probably studied this at some point. But yeah, when you square the trigonometric function, you cannot get a negative value. Okay. So basically, the cos square varies from 0 to 1. Now, when do you think the maximum kinetic energy can be achieved? When cos square is 1, right? When it's 0, kinetic energy is 0. And when it's a decimal value, let's say 0.1 to 0.9, yeah, it's not going to give you the maximum value. It's going to give you 0.9 of whatever the amplitude is, or 0.1 of whatever the amplitude is. When do we have the max? When cos square is 1. So I set cos square omega t as 1. And what do I get? The k max value, which is simply the amplitude. Simply the amplitude. So half m v max square, because a omega is maximum velocity. We just defined that previously. Now look, I have defined energy total or total energy as this, and I have defined kinetic energy as half m a square cos square omega t plus potential energy that we're going to find out. So we do a bit of not derivation, we do a bit of manipulation over here. And what happens is we end up taking this part common, that is this. So basically, I take this entire thing to the left hand side. Okay, follow me. So I take this entire thing, kinetic energy part, to the left hand side, and I have uh, this over here, and I have this over here. So potential energy went to the left hand side. Clear if you're following me? So now I have half m a square omega square minus this, which is half ma square omega square cos square omega t. Now what do I take common? This part. And when I take that common, I'm left with 1 minus this part. Clear? Fair. So now, what can you define 1 minus cos square omega t as? It's very simple. It can be defined as sine square omega t. Trig functions, trig identities, sorry. Trig identities, right? So I can define 1 minus cos square omega t as sine square omega t. Very simple, right? So now I have the expression for how potential energy changes with respect to time. How does it change? We see. This is how it changes. The orange curve. So sine square curve, right? What did we get? A sine square curve. If you plot in your calculator again, what you will see, sorry, in Desmos calculator, that a sine square curve varies from 0 to the max value in such a manner. Okay, so it starts from 0, goes to maxima, comes back to 0, goes to maxima, and so on and so forth, right? So this is how sine square varies. And notice again, whenever I add these two values, that is the potential energy and kinetic energy, I get this red line. Whenever you add both the values, you get the red line. That is the total energy line. And total energy remains constant throughout the journey. Okay. So what did we do? We have defined how kinetic energy varies with time and how potential energy varies with time. That is all that we did. Okay. Fair enough till now. Now, um, that is it. And 17.8 and 17.9, these are example videos where I have talked about how simple harmonic motion can be applied in a pendulum case, and we come across an equation for the time period. You can look at the video and you'll understand what I'm talking about. So basically, we find out the acceleration equation for a pendulum case. That is, acceleration is equals to minus omega square x from oscillation in simple harmonic motion. What you will see is in case of a pendulum, this omega is actually equal to mm, g by r. And this is an entire derivation. Okay, so when you go through that derivation, you understand why omega square is equals to g by r in case of a pendulum. So g by r is basically the constant, right? Such as omega square. Okay, so if you're confused about what I've just mentioned, no worries. If you just go through the derivation, you'll have a clear cut idea of what I'm talking about, right? Same thing we do with springs, right? And in this case, what do we get as omega square or as the constant value? We get the spring constant by mass. This is my omega square value, or A is equals to minus omega square x. A is equals to minus k by m x. So in case of a spring, this becomes my gradient. And in case of a pendulum, what is my gradient? G by r, or the constant value, right? So in these two cases, I did an elaborate derivation, showed you how you can solve questions in a pendulum scenario and in a spring scenario, that is mass and spring. These are the only two sort of questions you will get. Okay. And this usually is not elaborately taught to you. It is more or less a test of how you can do the derivation yourself in the exam paper. But I've included this and you can follow this through on the 17.8 and 9 videos. Okay. So that is a bit extra. If you wish to do it, do it. It will definitely help you when you're solving the papers of oscillation, without a doubt. Okay. Now, the last two bits of oscillation chapter, you have done more or less all the complicated parts. That is, the most important is the graph. In this chapter, one of the most important part is understanding the graph and the trig functions over there that you have. That is with respect to time and how velocity or acceleration varies with respect to displacement. These graphs are very important, or the energy graph. All of these graphs are very important in oscillation. You need to be able to read the graph. You need to be able to calculate from the graph. So do the questions. If you have any question that you're stuck on, really difficult question, let me know. I'll try to solve it. But read the graph, understand the graphs. The graphs will be one of the most important part in this chapter. Now, 17.10, which is damping. Okay, important chapter again. What do we have over here? Very simple. We are going to talk about the real case scenario in real life, that oscillations don't take place without any resistance. If I have any sort of oscillation taking place back and forth, there is always some amount of resistance. Wind or resistance at here in the pivot, any sort of resistance we do have. And sometimes we want to add resistance because we want to damp the system. One of the biggest example that I can think of and tell you guys of is earthquake. When such a tremor hits and buildings start oscillating, you want to make sure the building doesn't oscillate for too long or at a certain frequency such that the building breaks down. Okay, so two things we'll talk about: damping and resonance, two important chapters. So, what you don't want in some cases, I don't want the building to break down. And how do we stop that? We introduce damping. We'll make sure it doesn't oscillate. Okay, we will minimize the oscillation, minimize the damage. Okay, so that is why damping is important. And there are several sorts of damping: light damping, heavy damping, and critical damping. So let's say I want to talk about light damping. What is light damping? Let's say I go back to that same image. Light damping is basically a sort of procedure that you do where you want the bob or the oscillation to come to a stop eventually. Not immediately, but eventually. How so? Let's say this is the maxima and this is the other maxima on the left and right. So it starts oscillating, and then you want the oscillation to continue, but with lower and lower and lower and lower amplitude. And at some point, it stops oscillating. This is light damping, a case where the oscillation doesn't come to an immediate stop. The oscillation continues, and eventually, at some point, after some repetition of oscillation, it comes to an absolute stop. Okay? So what do we see over here in this graph? This is the amplitude, which defines the maximum position that the pendulum reaches, okay, on left or right. And the x-axis, let's say, is time. Okay. So now, initially, with this first oscillation, it had a certain maximum amplitude. And as it continued oscillating, the amplitude kept decreasing. Why? I just showed it to you. Maximum amplitude, damping is introduced, and it starts oscillating with less and less and less amplitude and eventually comes to a stop. This is light damping. And what you see, if you plot the peak, right? If you observe the peaks, it decreases with an exponential, inverse exponential nature. So we say this is decreasing at a rate of y is equals to e to the power minus x. Is this needed? No, you don't need to understand this. Not needed. But basically, just a bit of extra knowledge that it decreases with an inverse exponential nature. Okay, so it is a very timed out way, or where oscillations are repeated for several times with less and less and less amplitude. Okay, so this is one damping, that is light damping, where oscillation doesn't immediately come to a stop, but gradually comes to a stop.
Sir,
Right?
could you go
Yeah,
back a bit? I wanted to look
sure.
at.
This one?
Yeah.
Yeah. So over here, one more thing that I would add is frequency stays same
Sir,
throughout the journey. Yeah,
somewhere else, I read that it's defined as the gradual loss of energy. Is it like that?
yeah, you could say that. Because why does it say that? I will also show it to you. Um, where can I see the total energy? The reason it says that is, notice this. Ke max, I can also say this total energy, right? We just discussed this. Notice the amplitude. There is amplitude in this equation, right? So if my amplitude is decreasing with respect to time, my total energy is also decreasing with respect to time. So what you read is very accurate. It is the gradual decrease of the total energy of the system, right? This is why, because the amplitude keeps decreasing. So when you see this amplitude decreasing over here, from this to this to this is a gradual decrease of the energy of the system or the bob. Got it? Yeah?
Yeah.
Yeah. Any other question? Okay. So now Uh, yeah. So I was saying this is gradually decreasing of amplitude, and exponential nature is there attached over here. That is, it decreases with an inverse exponential nature. Okay, e to the power minus x or minus omega t. This is not needed for you. You don't need to worry about this. This equation doesn't come up. What you need to understand though is the qualitative nature of this damping. That is, it gradually decreases the amplitude, but oscillation continues until it comes to a total stop at some point. So, oh, the other thing I was saying is the frequency remains the same. What does that mean? So, let's say, first case, it oscillates between these two positions. This is minus A, this is positive A. Now, what happens is after one of the oscillation, the amplitude decreases and it goes to this position and this position. So now minus A1, let's say positive A1. So it has gone to a lesser amplitude. So now initially the bob oscillates from here to here, and then it oscillates to this new maxima, then this new maxima. Got it? So now what I'm saying to you is the frequency throughout the journey remains the same, regardless of the fact that amplitude has decreased. What does that mean? Whatever time was needed for this bob to go from positive maxima to negative maxima and this position, let's say 5 seconds, it will still take 5 seconds to go from this new positive maxima to this new negative maxima and equilibrium position. It will also take 5 seconds. So what am I saying over here? The frequency or the time period of the oscillation doesn't really change with respect to the light damping as it proceeds, as the oscillations proceed. Sure, the amplitudes decrease, but the frequency remains same. Okay, so the frequency of the oscillation remains same. Got that? Okay. Now, so this done. If frequency remains same, time period also remains same because one by time period, right? So vice versa, both are the same thing. Now,
So
next one, yeah.
do we need to know why it decreases that way? Like,
Why it decreases what?
why gradually the amplitude decreases like that?
Oh, this is simply the nature of light damping. It whenever it's like it's simply a statement that whenever you have a gradual decrease of energy or amplitude, that simply means it's lightly damped. Why it happens is because the damping is not strong enough to eat up all the energy of the system, which we will see in critical damping. So when, let's say,
Will we need to explain here, like explain the graph, explain the variation?
explain as in, I mean, you would have to say that it is gradually decreased. I mean, it is gradually decreasing, the amplitude is gradually decreasing, and eventually at some point the oscillation will stop. That is pretty much all you need to talk about. But you don't need to describe the graph as such. Like I've mentioned, it is envelope shaped or exponential decrease. It may ask you, and this is probably the max description you need to give in the sense of how the amplitude varies. But that is it. It won't. There's no elaborate description of this graph. This is probably the max you would be asked to say. Okay.
So this displacement against time or amplitude against time?
I mean, this is displacement against time. It's just that these position are the amplitudes. These position are the amplitudes, right? It is a displacement versus time graph. But this is an amplitude, this is an amplitude, this is an amplitude. Got it? You see
Correct.
the amplitudes in a displacement versus time graph, right? So
Yes.
I'm simply marking these as the amplitudes. That's it. Okay, right? Um, yeah. So basically, yeah, any other question?
No.
Okay. So now the next thing is critical damping. So what is the difference in nature? One is where, let's say I have this system, and the oscillation continues for a while until all of the energy gets eaten up, or all of that total energy of the bob gets eaten up. Now, in case of critical damping, what happens is, let's say there is some sort of friction over here, such that before, even if I displace it by this displacement, that is, let's say 5 meters, and I release it will slowly come back to the equilibrium and stop. That is it. It won't even go here. It won't even go to the left side. It will just very fast come back to the equilibrium position and stop. Why? Because there's some sort of a friction over here, some sort of a obstruction over here, some sort of a mechanism over here. Let's say there's a gear over there that it is resisting the motion to equilibrium position, and it is eating up that energy. So basically, in nature, what you asked right now, that why does light damping happen, or why does light damping look like that? It is simply the fact that whatever is eating up the energy, or whatever is uh, causing the damping, is not enough to entirely eat up all the energy, or waste all the energy, or completely stop the motion when it is coming back to the equilibrium for the first instance. So in light damping, it is less damping. That is it. That is why the oscillation continues. In critical damping, it is a lot more damping. So there's some sort of a mechanism that resists the motion back, right? So if this bob earthquake hits and the bob goes to the maxima, it's been pushed to the maxima, let's say, and now while coming back, it will very fast come to the equilibrium and stop. That is the mechanism in place. So that is the critical damping. It is simply the damping over there that causes this motion. That is it. So basically, what do we have? We have a system where it is critically damped, and it comes back to the equilibrium position, that is x is equals to 0, fastest possible time, as fast as possible. Okay? Let's say you have a car suspension and you went over a bit of obstruction on the road, and you don't want your car to sort of keep oscillating up and down. Okay, you want it to immediately come to a stop. You don't want your car jumping around as you move by the highway, right? So in such cases, you want the brakes to be geared in such a way that when the obstruction is hit and the system is moved beyond the equilibrium position, it will eventually, I mean, not eventually, very fast come to a steady position, or the equilibrium position for the car or for the gears. So that is where you need critical damping, right? You don't want the car to oscillate up and down. That is not convenient, right? So it's critically damped, and whenever the obstruction is hit and the tires are pressed, it very fast gains back the equilibrium position. Okay? So it goes from the amplitude to the equilibrium position. It does not oscillate. There you need critical damping. So anything that vibrates is an oscillation. You hit the pen and it causes a vibration. That is an oscillation. Okay? You hit your head and you feel a bit of a zzz. That is an oscillation. Right? Anything that you hit goes back and forth, causes some sort of a wave. It is oscillating, something that's oscillating, right? It's an oscillation. Okay? You see the ripple. Well, oscillation, technically. So now, point is, that is a bit of a deviation, but point is, when you have critical damping, you have the system coming back to the equilibrium in the shortest possible time without oscillating. Without what? Oscillating. Clear? Now, what is the feature? Well, it does not oscillate, directly falls to zero in the shortest possible time, and it has the fastest decreasing gradient. That is this gradient that you have. So it has the fastest decreasing gradient, very steep. That is the displacement against time. Okay. So yeah, it comes to a stop, and plateaus down at the x-axis. Fair. Now, heavy damping. What is heavy damping? It is very different to critical damping. This case, you have some similarity. That is, it does not oscillate after the first displacement from the equilibrium. That is, if it was at EQ over here, and this is the max displacement, that is amplitude, right? And time. Whenever you have that max displacement, it eventually very slowly comes back to the equilibrium. That is the difference. Very slowly is the difference. So even in this case, my friend, look, you have the oscillation such that, and oscillation, you have the damping such that the bob from the maxima comes back to the equilibrium, but very slowly. Not fast, not fast, very slowly. That is the only difference. So over here, the damping mechanism put in place is just different. Okay?
Sir,
Yeah,
does
yeah.
absolutely no oscillations take place, or like does it stop after a few oscillations?
No oscillation. No
Mm,
oscillation. No oscillation. In heavy and critical damping, no oscillation. It is displaced from the equilibrium and it comes back to the equilibrium. So the earthquake hits, it is displaced and comes back to the equilibrium. I mean, you can't really critically damp buildings in that nature, but damping is introduced in buildings. But point is, in critical and heavy damping, the oscillation doesn't continue. Okay, so the
So
first
this is the
oscillation takes
graph,
place and comes to a halt. Sorry.
and so this is the graph. Like,
Yeah.
why
So it
why
is.
does it
Look
look
at
like
the.
that?
Why does it look like that? So it has
Yeah.
a much lower slope. Like you have a steep slope over here, and you have a not so steep slope over here. It is more elaborate. Sorry, it occupies more of the x-axis. So what that shows is it gradually decreases, so that it coming back to the equilibrium position, it happens very slowly. So it doesn't it doesn't get shaken and doesn't immediately go to the equilibrium. It takes a lot of time. Okay, it takes a lot of time to come back to the equilibrium as in comparison to critical damping. Got it? So it's just what is the difference? The time consumed to come back to equilibrium position, right? So it's just the time consumed to come back to equilibrium position. Got it?
Yes.
Okay. So one example could be the door closing down. Yeah. So you have seen those, automatically closing doors. So that is one way I can explain it to you. Let's say you open the door and you want the door to shut, right? And you have displaced the door by some amount of a displacement, and it is now going to come back to the initial position, initial equilibrium position. And in that case, you don't want critical damping because someone who is behind you, it will simply hit their face. Okay, because in critical damping, it goes to the equilibrium position in the shortest possible time. Over there, you would want heavy damping. So you have displaced the door, opened the door, and someone behind you, while the door is closing down, can hold it and open it for themselves again. And over here, you also don't want light damping. If you open the door, if the door now starts going back and forth, that is very weird, and you don't want that. You don't want light damping in a door. Then the door will, if this is the door horizon, and if you displace the door by this, and it starts sort of oscillating, then the door is basically going back and forth between the two positions. That is light damping. And eventually, at some point, it comes to a stop. You don't want that. You want heavy damping in case of a door. Got it? So, do we see where and why these two sort of types of damping are relevant? Yeah. Okay. Mm, fair. So we understand how the dampings are relevant, okay, and how they're useful. Now, the last thing is resonance, right? In this oscillation chapter, the last thing is resonance. In case of resonance, this is a very important, not important, I mean, you can look at this video to see the physical description of
Sir, could I look
how
at
damping.
critical? Could you show critical damping again, sir?
Yeah, this one.
Oh, so it takes a longer time in heavy damping, right, to return to equilibrium.
Yeah, exactly. So that's just the only difference.
Okay, so
Okay. I've shared the link for this class's video. It will be automatically uploaded over here after the recording is done and uploaded to cloud. Okay, that is day 12 today. Yeah, should be day 12. Okay, so that is there. And I mentioned to a few people when mailed them, but basically, if you're sticking to the end of the batch, that is around first, second of October, I guess that's when the classes will end. If you're sticking to the end, you'll be given day to physics black book for consistently being there. Okay, that's a bit of a reward from our end. So hope that is helpful. Okay.
sorry, sir, what did you say, sir?
So basically, if you're sticking to the end of the batch till like 2nd October-ish and you have consistently shown up, you'll get the A to Physics Black Book from our end.
Oh,
Okay, it's just so. Hopefully that helps. This is basically what I'm using to teach right now. Okay, so you can use that before your exam. Hopefully it helps. And last thing for the oscillation chapter is resonance. Resonance is a bit of a simple thing, but if people don't see it, they don't really understand it. But before I show that video, I will give you a bit of a background of what natural frequency means. So basically, any object that you have, and mass and spring or pendulum, whenever you displace it, right, it oscillates. And it has a natural frequency of oscillating. Doesn't matter how much you displace it by 10 meters, 20 meters, 100 meters, doesn't matter. That is not a factor. What really matters is the type of the object you're displacing. Is it a strong spring? Is it a very weak or light spring with a less spring constant? So the type of the material determines at what frequency or what natural frequency the object will oscillate. So if you have your earlobe and you just push your earlobe uh, or hit your earlobe, you will see your earlobe sort of oscillates back and forth for a while, right? That's a very weird example. The point is, that is the natural frequency of your earlobe. Doesn't matter how hard you hit it or how much you displace your earlobe by, it will oscillate and come back to the initial position. And that frequency of oscillation depends on the kind of earlobe. So let's shift from earlobe to springs, let's say. And I have the same spring, one over here and one over here. Same spring constant. So don't get confused, right? It's the same spring, and once I displace it by 10 centimeter, okay, follow me. And the other case, I displace it by 20 centimeter from the equilibrium. Okay, fair. What happens is I plot the displacement versus time. Okay, so this one, case one and case two. In case one, what do I see? It at the initial equilibrium position, it has displacement 0, goes to maxima over here, and then goes to a minima over there, somewhere over there. So it strings, that is this position, and then comes back to equilibrium, that is this, goes to maxima, that is this, comes back to equilibrium, that is this, and goes to minima, that is this. So you see what I have plotted, right? You exactly see what I've plotted. Same thing I do with this, the one where I have displaced by 20 centimeters. Okay, so I have initially 0 displacement, then 20, then 0 again. So this is 0, So 20, that is this, then comes back, there's 0, and then goes to 20 again. This is a bit is not to scale. So the fixed point should have been somewhere up there, okay, so that it has space to sort of shrink or compress. This is not the perfect diagram for explaining that, but anyways, point is the uh, mass will compress and reach somewhere around here, 20 centimeter above the equilibrium, and then that is this position, and then come back to equilibrium, that is this position, go to maxima again, that is this position, right? You get the idea. You get what I'm doing, right? You get what I'm doing. So basically, I have plotted the displacement versus time. What do I see? Why am I saying this? What do I see in these cases? What I see is in case one, the time taken for the mass, granted these are same masses, so 1 kg, 1 kg, let's say. So in both of these cases, it took the same time to complete one oscillation. Register that. Register that. In case one and case two, regardless of how much I pulled down the mass, in both cases, it took 2 seconds to complete one oscillation. Okay, understand that. So, what this means is this spring has a certain natural frequency. Has a certain what? Natural frequency. Doesn't matter how much you pull it by, it will oscillate freely. It will oscillate freely at a certain natural frequency. Granted, you are not pushing the mass up and down with your hand consistently, and you just pull it down and release it, it will oscillate freely with a natural frequency. And these two objects have a certain natural frequency. How do I find that? Number of oscillation, or let's say we have one oscillation, how long it takes? 2 seconds. Okay, so how many oscillations do we have per second? Right? 0.5 per second. I have half the oscillation, because if it takes 2 seconds for one complete oscillation, in 1 second it completes one oscillation. Simple math. Similarly, over here, it is one oscillation every 2 seconds. So frequency is 0.5 hertz. Got it? So this is the notion of natural frequency, my friend. You need to understand that. Every object has a certain natural frequency. Okay. So it doesn't matter how much you displace it by. And you will ask me right now, what is the natural frequency? How do I find it? Depends on what system you're working with. You're working with a mass and spring system. You're working with a pendulum system. Depends and differs. So if you watch those two videos, you will understand how to find the time period. Okay. First, you find out omega square, that is whatever the omega square value is, and then you find out omega. So you take a root of whatever is over here, and you define omega. And then what do you do? You know omega is 2 pi by t, and that is equals to root over whatever the expression is inside. So now you make t the subject and find the time period. So if I just want to show it to you, a glimpse for you guys, 17.8, right? Over here, I found out my omega square resonates with g by r. Okay. So my omega becomes root over g by r. So what does wait, I'll ask that later. So omega becomes g by r. So 2 pi by t is root over g by r. So my time period is simply 2 pi root over r by g. So if this is time period, my frequency is 1 by 2 pi uh, g by r. Sorry. So now my point that I'm trying to make over here, what does my frequency depend on, or the natural frequency? It depends on the gravity and the radius. This is in case of pendulum, by the way. So in case of pendulum, the value of gravitational field strength and the radius determines my natural frequency of the pendulum. Okay, that determines the natural frequency of the pendulum. Got it? Got it? So every object has a different natural frequency. Every object has a different natural frequency. Okay, and we determine that by using by comparing the omega square value to whatever the constant is in whatever system you're working with. In pendulum, this is G by R. In case of mass and spring, it's probably K by something, K by mass, yeah. So K by mass, K is the spring constant. So it differs with different scenarios, right? So you basically equal the omega square and this constant that you have, and then you make time period the subject and you find the expression with respect to time period. And now it's easy for you to find the frequency because frequency is 1 by time period. And whatever frequency you find over here is the natural frequency. The frequency that the object oscillates at naturally. Okay? The reason I'm stretching that so much is because that directly links with resonance. Okay, how so? Look, natural frequency of an oscillation is only achieved when the system oscillates freely. Okay, so basically, it's the frequency of an oscillation when the oscillating system is allowed to oscillate freely. Got it? Now, what is a free oscillation? It is an oscillation where there is no external force acting. Hence, no energy input is provided. Energy is not lost as no damping exists. This is a free oscillation. Where energy is not lost, energy is also not provided. Okay? So it's a very conserved system where the object oscillates freely. Okay? Now, what is a forced oscillation? I'll show this to you. But basically, it is where the oscillation is driven by a periodic force applied to sustain that oscillation. Let's say you have a child on a swing. You have to keep pushing the swing to make sure it reaches the same amplitude at every oscillation. Because naturally, there is a bit of uh, friction over here at the pivot. So you want to make sure that there's someone pushing the swing back and forth so that it is a driven oscillation or a forced oscillation such that it can continue reaching the maxima, positive and minimum maxima, so that the child keeps having fun and does not come to an absolute stop, right? So that is pretty much the point that you have some sort of an external factor pushing the oscillator to oscillate. That is a forced oscillation, right? So when the oscillation is forced by external factors, then the frequency of the oscillator is known as driving frequency. So basically, let's say I have this mass and spring system, and I basically this is mechanized, and there's a bit of a gear involved over here, and I have basically um, connected to some sort of power supply such that this fixed point moves up and down, and this provides the driving frequency. So with respect to what frequency this fixed point moves up and down, my mass will oscillate up and down. Got it? So this is how you can provide the driving frequency. Now this is where things get interesting. Up till now, by the way, what I showed over here is how the driving frequency works, or how externally we can change the frequency of the mass. So basically, if you just pull this down and it oscillates, the frequency that it will oscillate at is the natural frequency. But if you externally move the point over here and make it oscillate, then that is the driving frequency. So if I'm moving the, let's say, the fixed point, the gear over there, at 5 hertz, the object or mass will oscillate at 5 hertz. If I move the fixed point at, let's say, 10 hertz, the mass will oscillate at 10 hertz. So this is not a free oscillation. This is a forced oscillation, where the oscillation, the force, is consistently and constantly provided. Okay? So this mass does have a natural frequency, but when it's a forced oscillation, that is not respected. Got it? Okay. Wait. So, as I was saying, there can be a driving frequency by external factors. Now, understand that every object has a natural frequency. Believe me. And sometimes we force objects to oscillate to overcome the damping or the friction forces. For example, the child and swing example. Now, when external forces are applied, the object will have a frequency known as driving frequency. So whatever frequency I oscillate this at is the driving frequency. 5, 10, 15, whatever the frequency may be. And when this driving frequency is the same as the natural frequency of the oscillation, resonance is achieved and maximum amplitude can be seen. What does that mean? So whenever, let's say, this has a natural frequency, this system has a natural frequency of 10 hertz. I'm telling you that. I know that. And I make the gear oscillate at 10 hertz. You know what will happen? Resonance will take place. What does that mean? This box over here, this mass over here, will move up and down with the maximum possible amplitude. So if the driving frequency was 5 hertz, it would probably oscillate this much, like this. And if I increase the driving frequency to 10 hertz, that is of the gear, it would oscillate something like this. So the amplitude all of a sudden has increased. That is the energy transferred from the driving frequency or the fixed point to the mass has increased. I repeat, the energy transfer from the fixed point or the gear over here has been maximized to the mass. I repeat yet again, the energy transferred from the gear over here to the mass is maximum when driving frequency equals natural frequency. Be clear on that. So when you have resonance take place, that is driving frequency equals natural frequency, the energy transferred from the from the gear or the mechanism is maximum because both are oscillating at a frequency that is an exact match of the natural frequency. And in that case, the energy transfer is maximum from the machine to the oscillating object, that is the mass. That is why the amplitude all of a sudden is maximum because it has higher energy. Okay, so that is what's happening. At resonance, energy is transferred from the driver to the oscillator most efficiently. At resonance, maximum kinetic energy can be seen. Okay, and this is the definition of resonance. Okay, I'll show you something right now. Notice, I'll go here. Let me show you something. So if you're following me, I'm seeing my screen. Hopefully you can see my screen. Notice this. I'm telling you guys, it is at 9.10 hertz around. Notice the frequency. Notice the oscillation. So it is oscillating with a certain amplitude up and down. That is a bit sideways, right? And now all of a sudden, wait a minute. At 15 hertz, I see. Why is this quality so bad? Hmm. All of a sudden at 15 hertz, do you see the increase in amplitude? It is now oscillating with a much higher amplitude. much higher amplitude as compared to a lower frequency at 10 hertz. Notice 10 hertz, lower amplitude of oscillation. Now, what happens if I increase the frequency beyond the natural frequency? So at 26, notice 31, 32. Do you see the amplitude having decreased? The amplitude has decreased. The amplitude has basically decreased. What does this mean? So when you're below the natural frequency, that is of the driving frequency, resonance is not achieved. And when you are higher than the natural frequency, that is of the driving frequency, resonance is also not achieved. It is exactly at the natural frequency when resonance is achieved and maximum amplitude can be seen. Otherwise, resonance is not achieved. Any questions on that? Are we clear on that? Give me a thumbs up. Okay, perfect. So that's why resonance is important. The match of natural and driving frequency is important. That is when maximum energy transfer can be seen, right? So now let's look at the graph. How does sort of the driving frequency vary the amplitude with respect to natural frequency? And I'll repeat what I just said if it was confusing way of structuring it. Let's say I am changing the driving frequency that is of the fixed point over here. That is one case. I just showed you another setup, right? This is one setup. I mean, not necessarily as a setup. I'm just explaining it to you guys. But you just saw a video where the setup was very different. So it can be any sort of setup. It doesn't really matter. Point is, as long as you understand what the meaning of natural and driving frequency is, you'll understand the rest of the stuff. So over here, what I've really plotted is how the amplitude changes as my driving frequency changes. Again, so if I have this system over here and I have a mass over here, and the amplitude will vary as I vary the driving frequency over here. So on the x-axis, I have, sorry, on the y-axis, my bad. On the y-axis, I have the amplitude of the mass. Maximum displacement that the mass will have in the oscillation. That is the amplitude. So I have the amplitude on the y-axis, and on the x-axis I have what? Driving frequency. Okay. On the x-axis, I have the driving frequency. Clear? So basically, I am changing the driving frequency from, let's say, 0 to some value infinity. And I'm seeing or observing how and when I see maximum amplitude of the mass. Again, I repeat, I am increasing the natural or sorry, driving frequency, not from 0, it's some value over here, from a certain value, x, uh, to, let's say, infinity, some value. So what I want to observe is at what driving frequency do I get the maximum amplitude? Okay. At what frequency I have the maximum amplitude. So I'm changing the frequency of this, and I want to observe at what frequency this mass starts moving up and down violently. That is with maximum amplitude. That is what I'm observing. Granted, you understand what the graph is. Moving on, I plot the graph, and what I observe is, yeah, basically when it's not in your syllabus, but it's the nature of the object. That is when your frequency has increased so much that it wants to complete that one entire oscillation in a lower period of time. So the amount of distance it is covering becomes less. That is one way to explain it. So basically, the amplitude starts decreasing very fast. So because notice this, if my frequency wants to increase, my time period has to decrease, right? So it wants to. That's a qualitative explanation that I'm giving to you. So basically, it starts covering less distance on lower amplitude. So what you see is a steep decrease. So it's covering lower amplitude, right? So that is why, to an extent, I can say that is why it's happening. So it's starting to vibrate really fast, right, with a higher frequency. So it wants to cover a less distance or a less amplitude so that it can do it in a less amount of time or increased frequency. So time period is decreased, frequency increases, and amplitude, ideally in this case, when the frequency is beyond the natural frequency, is so the number of frequency is increasing. Uh, and the amplitude becomes less because you want to cover more oscillation within the same period of time, right? So that is essentially one way to answer your question. Does it satisfy what you asked? Yeah.
Sure.
Mm.
Um,
Okay. Yeah.
could you go up a bit or to write it
Yeah.
down?
Which part? Resonance?
Yeah, the first part, the first page of the resonance,
Sorry, sorry.
the first part of resonance frequency, the first page.
This one.
Yeah.
Okay.
All right.
Okay. Okay. So, I mean, okay, what you asked, I could also give you a bit more insight. So you have studied, what did you study in AS? You have studied destructive interference, right? And constructive interference in AS, I guess. Yeah, in waves chapter and superposition, probably. So basically, the conversation sort of becomes somewhat along those lines where we have a bit of the energy transfer, between this oscillator, sorry, not oscillator, this driving frequency and this mass. That energy transfer becomes less efficient and it happens very fast. Why? Because there's this notion of destructive interference, the rate at which the oscillator wants to transfer energy and the rate at which um, uh, the mass wants to naturally vibrate at is very different. And it's sort of out of sync, which is why energy transfer is what? Less. Which is why amplitude becomes less. Got it? So that is why beyond the natural frequency, when I increase the driving frequency, the energy transfer decreases a lot. Okay. And that is why you see this steep decrease beyond the natural frequency. Okay. So it is not as different as this side. It is just that you see a gradual increase over here, and it's somewhat equal around the peak. So if I show it to you, this is a typical graph that came in your question. It is not as different, but basically the nature from the beginning to this part is different to the nature from this position to over here. Okay, but it's still somewhat similar. Okay, it's still somewhat similar. So the logic of the lack of energy transfer applies both in this case and in this case. Okay, so depending on what system you're working on, right? Depending on what system you're working with, the shape of the resonance curve can vary. Okay, so the shape of this amplitude versus frequency, driving frequency, can vary. And For example, if I have a spring with, or a spring system, or that is a spring and mass system, or a pendulum system, or the experiment that I just showed to you guys, depending on the system and depending on what the type of, let's say, the spring is, that is what spring constant it has, the value, the natural frequency value will change. Okay. And the gradient on either side of the peak will also change. And I will show that to you guys over here, where you will notice the variation more vividly. Okay, so yes, valid question. Why does it decrease differently on either side? It's simply the phenomena of how the energy transfer is taking place. Okay, it is just that conversation. And in one case, the energy transfer is more efficient in comparison. In another case, energy transfer is less efficient. And there are multiple reasons for that. You can talk about, constructive interference, where it's easier, or the frequencies are same and it's easier to sort of transfer the energy, or it's sort of out of sync and it's harder to transfer the energy. So a lot of in-depth conversation can take place over here. If you're interested, you can look into it. But yes, the main few features of this graph that I would like to go over is, before the natural frequency, the amplitude is increasing, right? So from a lower driving frequency to meeting the natural frequency, I have my amplitude increasing. The moment my natural frequency has been met by the driving frequency, the amplitude starts decreasing. And you saw that in the video, right? Why? Because they are now out of sync, or in nature, I can say the energy transfer between the driving frequency and the mass is less efficient. So now the amplitude, by the way, again, amplitude is a definition, or it defines how much energy the system has, right? So the energy transfer becomes really inefficient. And again, the amplitude decreases. And one more thing I will flag post is, don't go by this shape and say, oh, well, this is how typically all resonance curve should look like. No, it can be different. Okay, it can be very different. It depends on the system. It depends on the type of the materials you're working with. Okay, so yeah, second, but that's done. And the second thing is, what happens at f is equals to that is driving frequency is equals to natural frequency. You see the maximum point, that is maximum amplitude is achieved because maximum amount of energy is transferred, right? So over here, maximum amplitude is seen, resonance is achieved. Now beyond this, when driving frequency increases beyond natural frequency, starts decreasing. Okay, you understood why, all of that, and you see the shape, you understand the shape as well. Uh, and now, what happens if I introduce damping? How does the shape vary with respect to damping? Let's say I introduce some amount of, let's say, light damping, or heavy damping, or critical damping. What happens in each of those cases, right? So let's say I have some low amount of damping. What happens in that case is, any amount of damping introduced, any amount of damping introduced, the peak amplitude will reduce. It starts decreasing. Okay. So whenever you introduce some amount of damping, your amplitude starts decreasing. And what you will also notice is the natural frequency of the object decreases as well. So if I have a system as such as this, and I introduce some sort of damping over here, you know what happens? The natural frequency, that is, if I pull it down by this amount and make it oscillate, naturally it will start oscillating at a lower frequency due to the damping. So the natural frequency gets reduced. That is why you see this shift on the left hand side, or towards the left, right? So basically, the graph shifts to the left side as more and more damping is introduced. and the peak also decreases. So if you connect the peak, you see some amount of this uh, representation. That is a red line, the red dotted line. That shows how the peaks vary with respect to damping. Okay. So basically, I have uh, different amounts of damping, right? Different amounts of damping. And that different amount of damping results in different amplitude and different natural frequency of the object, right? So this is how the graphs will change. The last thing I want to show to you is over here in this question, they asked you that is there damping in this system? And your answer is yes, there is. Yes, there is. Why? Can any of you tell me? Why do you think damping exists in this case? Just by looking at it. So we have amplitude versus frequency, driving frequency. Any idea? Why do you think damping exists over here? And by looking at what do we determine this damping? No? Fair. So first time I answered this, I also didn't have an answer. Point is, it's very, I don't know, I found this very out of nowhere because it was not mentioned anywhere. But point is, it's not as sharp. So this peak that you see, it's not sharp. It is a bit blunt. And that sort of determines or shows you that there's damping involved. So when there's no damping, this peak should be very easily identifiable, and it should be a sharp peak, which shows there's no damping. Okay. And when you introduce some amount of damping, what happens? The, the peak gets shallower, right? More spread out. That is what we see with respect to damping, right? So from this point, from this to this to this, what is the difference? The peaks are being a bit more shallow, or in other words, in sorry, in other words, basically, you have a more spread out, or the steepness of the gradient on either side are less. So more steep over here, less steep over here, even less steep over here. Got it? So that is one way to look at it. So basically what I had asked is over here, is there damping or no? And the answer is there is damping. Why is there damping? Because this peak is blunt. And what this shows to me is damping has been introduced, because if there was no damping, the peak would have been sharp. Okay, get it? So whenever you see a sharp peak, that means there's no damping. Whenever you see somewhat of a blunt peak, that means damping has been introduced, right? Again, as more and more damping is introduced, the peaks become shallower. That is sort of the difference with respect to each of the damping case scenarios. That is one of the question. And otherwise, you have covered the entire oscillation chapter. The only thing I recommend, and I had posted previously, look at 17.8, look at 17.9, understand the scenarios of when, sorry, yeah, when and what equations we use for pendulum and for spring systems. Now, the next chapter I'll give you a bit of an introduction is electric fields. Okay. So this is what we will continue fully in the next class and with great depth. But in this class, I give you a bit of introduction, and that is electric field. What are electric fields? Now, you will sort of relate this to gravitational fields, where the core idea has not really changed. We're still working with force. We're still working with distances. We're still working with uh, a certain object, either mass or charge, exerting that force. So over here, we're working with charges mainly, positive, negative charges. And the difference over here in electric fields as comparison to a gravitational field is electric fields can have attraction or repulsion. So when there's attractive force, that is, one is positive, one is negative, they pull towards each other. When there's repulsion, they push each other away. Okay, so those are the different case scenarios we have. So the few things that I want to talk to you guys about is for any 2 point charges, right? You have heard about point mass particles, right? Point masses. The reason we make that approximation is because we concentrate all of that mass into a single point, that is the center of the object, right? Center of mass. And in these cases, these are like point charges. So let's say like one single positive charge, one single negative charge. That's how I'm defining the charges, right? So 2 point charges, if they have the same or different sign, each will feel a certain amount of force, which is going to be same for both. So let's say I have Q1 over here and Q2 over here, right? And I say both are positive charges. So case 1, both positive, clear? Both are positive and same charge. Okay, so it has 5 Coulomb of charge, it has 5 Coulomb of charge. And those are same charges, so what will they do? Push each other away or pull towards each other? Push each other's away. Okay, there's a repulsive force, same charge. So now the force that this applies, Q1 applies on Q2, let's say 10 newtons, I'm just arbitrarily putting these values, and the force that Q2 applies on Q1 is also 10 newtons. Newton's third law. Every action has an equal and opposite reaction. If Q1, this is a vacuum, let's say, if Q1 is applying 10 newtons of force on Q2, repulsive force, Q2 will also apply the same force on Q1, but in the opposite direction, right? So now, case 2, both are positive, but different charge. What happens then? They say this is negative. Still 5 Coulomb, still 5 Coulomb. Uh, my bad, my bad. I've written something, I've shown something. Oops. Let's say this is 10 Coulomb. So same charge, but different, same type of charge, positive, but different amount of charge. So one is 5 Coulomb, the other is 10 Coulomb. What happens in this case? Let's say the value has changed. So I tell you that Q1 applies a force of 12 newtons. What do you think? What force does Q2 apply on Q1? Give me a wild guess. What force does Q2 apply on Q1? Just write it down over here for now. What do you think? What is the force of Q2 on Q1? If Q1 applies 12 newtons on Q2. Anyone? Yeah.
Sorry, say again.
So what is the force Q1? Sorry, what is the force Q2 applying on Q1? Granted, Q1 applies 12 Newton on Q2.
Also
So
12.
Q1 is applied exactly. So basically, regardless of the fact that they have different charges, different amount of charges, they will apply the same force. It doesn't matter if they have different amount of charge. If one is applying 12 Newton, the other will also apply 12 Newton. Okay? So the amount of charge doesn't matter. Does the sign matter? Does it matter that one is negative and the other is positive? Nope. It's simply that now the Q1 will attract Q2 by 12 Newton. And Q2 will attract Q1 by 12 Newton. So my point is the force applied is always equal and opposite. Yeah, direction changes when the charge signs change. Q1 initially was when it was same charge, it was pushing it away. So pushing it away. So both were pushing each other away. And what happened next was I changed the sign, and now Q1 is pulling Q2 and Q2 is pulling Q1. So yeah, the direction of force changes when the sign changes, but in both cases, the forces applied on each other are opposite. Get it? So this should be clear that the force is applied regardless of the amount of charge, regardless of the sign of charge, is always equal and opposite between the charges. Same case with mass. It's just that in case of masses, in case of gravitational field, it was always attractive. The only variation that you have in electric fields is charges can be different and there can be attraction. Sorry, there can be repulsion. That's the only difference. So now if they have same sign, they repel. If both are different, then they attract. That is clear. Now, I will end today's discussion with Coulomb's law. Pretty much the bane of this entire chapter, right? And the entire conversation here is that I defined I defined this force, Coulomb force, that is the electric force due to charges existing by the following relationships. Sorry, these two maybe. So there's a relationship between the force and charge, and there's a relationship between force and distance between the charge. I have a charge over here. I have a charge over here. Q1, Q2. Okay? Sign and all that doesn't really matter. Let's say both are positive. And the amount of charge can be different. Doesn't matter. Can be different. Now, the conversation I want to have with you guys is it turns out to be by experiment that the force that Q1 applies on Q2 and the force that Q2 applies on Q1 equal, right? So if this is FQ1, right, and this is FQ2, not curved arrow, right? So these are the direction of forces, and these are equal. FQ1 equals to FQ2, right? So my point over here is, it turns out to be that if I increase the charge, either Q1 or Q2, it just so happens to be that the force also increases. So what I found out by experiment, or the scientists back then found out, is as I increase either of the charge or both of the charge, that is the amount of the charge, my force exerted by Q1 on Q2 or Q2 on Q1 increases. Force applied increases. So I find this relationship that force is proportional to the product of Q1 and Q2. Either Q1 or Q2 increases, the force on both increases. Doesn't matter which you increase or both you increase, force increases. The other relationship that I find out is the distance relationship. As I increase the distance between the charges, it just so happens to be that the force also decreases. I increase the distance between the charge and my force decreases. And by what proportion? By inverse square proportion to the separation. This. So my force decreases with an inverse square separation proportion. A lot of words. So as my separation increases, my force decreases by a square proportion. Okay. So if my radius goes from 1 meters to 2 meters, my force will become 1/4. Got it? So if it goes from 1 to 4, so 4 times the distance, let's say 4 times the distance, what will happen now? It will become 1/16th the force of initial force, that is, the force that it had when it was 1 meters away, as comparison to 4 meters away. So when 1 meters away, it applies a force F. When 4 meters away, the force applied is 1/16th of F. That is the initial force. That is the inverse square law, if you've forgotten from the gravitation chapter. So now the conversation is, if my force is proportional to the product of both charge, and F, the same force, is also proportional to the inverse square of the separation, can I not combine those two? Sure as hell I can. Now when I do that, I find out force is finally proportional to the product of both charges and the inverse of separation squared. Fair. Now what happens if I remove this? I have to introduce what? A constant. Fair. And that constant, I say, is K. Do we know what K is? If you say Boltzmann constant, you're wrong. K is not Boltzmann constant over here, that's in chemistry. So K over here is a different set of value. So what is the constant K? It is 1 by 4 pi epsilon naught. Experimentally found out, my friend. So basically, what they probably did was they plotted F against, let's say, Q2, right? And the gradient of that graph was KQ1 by R square. Okay. So what they did was plotted F. I'm giving you an example. So they plotted F versus Q2. So they changed the charge, and whatever they found as the gradient of the curve, M is equals to K Q1 by R square. So Q1 is known by them, that is charge of the other charge, I mean, amount of charge of the other charge, and the separation is also known by them. So they kept the separation constant, they kept Q1 constant. What they didn't know was K. So this is how, since you know the gradient of the line and you know Q1 and you know R square, you find out the value of K. Okay? So that's how we find out K. And they also saw that in different mediums, air, solid, and liquid, or any sort of difference in medium causes a different K value. Is that relevant for you? To an extent. So what they saw was K is not just a constant. You can't just say this is K for everything. Nope. They found out K is a combination of other things, which can be said as 1 by 4 pi times epsilon naught. And the main part is the epsilon naught. Because they found out, well, my K is actually changing with the different medium. What that means is when I have Q1 and Q2 in, let's say, liquid, when the charges interact in liquid, the force applied is different. And when my charges are in, let's say, solid, the force applied on each other is different. Again, when the charges are in air, the force applied on each other is different. Why is that? This constant K does not remain same in all of these mediums. Why? They did something smart and found out that K is actually, why does this slip? So they found out that K is actually a combination of 1 by 4 pi epsilon naught. And this epsilon naught is very important because this determines the variation medium. So what is E naught, epsilon naught? It is the permittivity of free space or vacuum permittivity. So this is defined as farads per meter. It is not exactly in your syllabus, But just to give you a bit of insight, when you have different mediums, charges interact differently. So when you have, let's say, going from vacuum to liquid to solid, the charges get to interact differently due to the medium coming in between of the interaction. And that sort of distorts or um, affects the charge interaction, right? So the force applied on each other, Q1 and Q2, differs with respect to the medium. Okay? So it's different in solid, different in vacuum, different in air, different in liquid. So, point is, we're mainly going to work with vacuum. And in vacuum, this is the value of K. Okay? So 1 by 4 pi epsilon naught, this is the value of K. Okay? And the value of E naught in vacuum is this. So if you just multiply 1 by 4 pi E naught, you will get 8.99 into 10 to the power 9. Okay. So point is, now I have defined all of the variables in the equation. So when I combine all of these together, I finally have F is equals to Q1 times Q2 divided by separation squared times 1 by 4 pi epsilon naught, which is what? The constant. Okay. 1 by 4 pi epsilon naught is K. Fair? Right? This is your final equation of force applied on charges. Okay. This is the Coulomb law. Force between 2-point charges is directly proportional to the product of their charge and inversely proportional to the square of their separation. If I had to plot the force is separation, how would it be? It would simply be F by separation. So it's an inverse rule. If you know y is equals to 1 by x squared curves, it'll be easy. It looks something like this. So as my separation increases, my force diminishes or decreases. Okay? And with a square relationship. Okay? So this is how force versus distance looks like. Next class onwards, we will talk about electric field strength and so on and so forth. So till now, any question, anything else that you want to know? 11 minutes or I guess, yeah. Anything you guys are confused about? Otherwise, we're done for today's class. Okay? Any questions? No? All good? Yep. Okay. So we're done for today. Next class is well, not sure. On Thursday, I guess. Let me see. Yeah, next class will be on Thursday, 11th, and we're gonna continue with electric fields. So see you guys on Thursday. Hopefully, no question. I'm gonna end the meeting. If you have any question, do let me know. No worries. Hope to see you all next class. Best of luck. Bye bye. See you guys.